Hello everyone, welcome to Aero 3240 Orbital Mechanics. My name is Professor Steve Ulrich and I will be your instructor for this course for the fall semester. So quick bio about where I'm coming from and my past experience. I got my bachelor and my master's degrees both in electrical engineering from the Université de Sherbrooke. That was in the early 2000s. And then I was fortunate enough to be hired by my thesis supervisor right after my master's degree. So his company is called NGC Aerospace, also located in Sherbrooke, where I worked there for a little over 2 years as a spacecraft guidance, navigation, and control research engineer, primarily working on Earth observation missions, doing the software for the onboard computers. So that was a lot of fun, and also during that period of time, I was fortunate enough to get a scholarship to attend the International Space University in Beijing, China, where over the course of a summer, I studied various aspects of space exploration. So, as you know, space exploration is not only about the engineering aspect, there's also the medicine aspect for human spaceflight, also management, science, physical sciences, outreach, things like that. So all aspects inherent to space activities. So it was a lot of fun. But then I realized that I wanted to really dedicate myself to research eventually. So that meant that I had to go back to school to earn a PhD, which I did. So I graduated with my PhD in aerospace engineering from Carleton in 2012. And then immediately after, I was hired by the MIT Space Systems Lab in Cambridge, Massachusetts, down in the States, where I worked as a postdoc, leading the Spheres activities on the International Space Station. So essentially, Spheres is a lab where we had three nano satellites maneuvering around the Japanese experiment module of the ISS. And these spacecraft or small satellites were used to experimentally validate novel computer vision, robotics, as well as guidance, navigation, and control software to enable future space missions. So that's a pretty unique facility that we had access to as researchers at MIT. So the plan was for me to spend couple of years at MIT Space Systems Lab, but then I saw that there was an opening at Carleton University and they were looking for a professor in the space systems area. So I said, oh, well, I better apply if I want to become a professor at one point in my career. And I was lucky enough to get the position. So I came back to Carleton in 2013, just after a couple of months at MIT. So I came back as a prof. And the first thing I did at Carleton here was to establish my research lab called the Spacecraft, Robotics, and Control Lab, where the main purpose of the lab is to develop innovative guidance, navigation, and control systems for spacecraft, as well as deriving algorithms to control robotic arms in space and doing computer sciences as well for developing novel computer vision software so that spacecraft can autonomously maneuver in space without the need of ground controllers. So typically my research team comprises of about 10 to 12 highly qualified personnel, so ranging from undergrad students all the way to research staff and in between PhD and master students. Currently, I have a lot of people in the lab. I have three research staff. These are recent alumni of the lab that are dedicating their time to help out grad students carry out their experiments in the lab and other aspects as well. But mainly the core team is comprises of 5 PhD students, 7 master's students, 1 MEng, so Masters of Engineering, as well as 1 undergraduate student in the lab. Over the years, my undergrad and graduate research students have accumulated various achievements, among them 4 Senate medals for outstanding research thesis, more than 15 graduate scholarships, typically from OGS, which is the Ontario Graduate Scholarship Program, and the NSERC scholarship program as well. Altogether, we published more than 100 publications, peer-reviewed publications in conference proceedings and journal articles as well. And we've raised more than $700,000 in research funding, which allowed us to establish quite a novel and unique experimental testbed and lab that I'll talk about in the next slide. So most of my research activities, or our research activities in the lab, are done in partnership with other organizations. Typically in Canada, we're talking about DRDC, which is Defense Research and Development Canada, MDA Space Missions in Brampton, that's the company that developed Canadarm1 and 2. NAPTEC here in Canada on the computer vision side of things, and obviously Canadian Space Agency and various other organizations in Canada and around the world. So in terms of the research activities that we work on in the lab, fall under two main categories. The first one is spacecraft formation flying, so that's something you'll learn more about in this course, where we are not looking at one spacecraft orbiting the Earth. That's not the purpose here, but what we're interested in too is the relative motion between two spacecraft orbiting the Earth. And we, under this team, we developed novel dynamical model that represents the motion between those two spacecraft, as well as deriving innovative guidance, navigation, and control systems that enable them to perform autonomous tasks while in space. The other research team that we're heavily involved in is called Spacecraft Proximity Operations. So it's very similar to formation flying in a way, because we're dealing with two objects in space. Could be an active chaser orbiting around say a space station, or getting close to a space debris, for which the purpose would be to capture it and deorbiting it at one point. But the main difference between formation flying and proximity operations is the distance that exists between the two spacecraft, or the spacecraft and another object. So formation flying, typically we're talking about 100 or 50 kilometers of separation distance, whereas proximity operations is really when the two objects or the two spacecraft are really close to each other, so that they're about to do rendezvous and docking maneuvers, and they have to do collision avoidance as well to make sure that they don't bump into each other. Under this research team, we do a lot of space robotics, where we design control algorithms to maneuver a robotic arm attached to a spacecraft. We do computer vision. We do path planning to design an ideal trajectory for an active spacecraft to follow in the vicinity of an unknown object. Could be a piece of debris or something like that. And the beauty of it is that we have a facility that I talked briefly about in the previous slide, which is Spacecraft Proximity Operation Testbed, or SPOT for short. So SPOT comprises a large granite table, 8 feet by 12 feet, and it's 13 inches thick. It's one giant granite table, essentially. Very smooth, very flat, on top of which we float two spacecraft platforms, pictured here in the figure. So the way that it works is that both platforms are fully autonomous. They have their own power system, they have their own computers, propulsion system, flotation system, because both platforms are not touching the table when they are operating. So they float right on top of the surface. We're talking about 5 microns of flotation height. So you would swear that they're touching the table, but they aren't. And that allows us to emulate the dynamics of space, which is nearly friction-free. So if you were to push one of these platforms on a table, it would, just keep traveling at a constant speed in the same direction, which is a good test bed again to emulate the space environment. Okay, enough about me and what I do for a living in the lab. So let's talk about the course, Orbital Mechanics. So it's worth understanding the way that the motion of a spacecraft orbiting the Earth or any primary body is explained. So we have two types of motions. First one is 3 degrees of freedom translational motion. The other one is a 3 degree of freedom rotational motion. And altogether that means that a spacecraft has indeed 6 degrees of freedom, 3 translational motion and 3 rotational motion. Roll pitch, yeah. The scope of this course will be limited to the translational motion. Okay, so we're going to talk about the trade-off translational motion only, and we're going to disregard the rotational motion. So in other words, we're going to consider that both the spacecraft and the primary body around which the spacecraft is orbiting are both point masses. Okay, so this is going to be the focus of this course, whereas the rotational motion, and this takes place whenever we consider the spacecraft as a rigid body, will be the focus of the follow-up course, which is Aero 4540, which is spacecraft attitude, dynamics, and control. Okay, so again, point masses for the time being, a translational motion only. So the content of this course is organized in 5 chapters. Chapter 1, kinematics and dynamics, will be I hesitate to say the most difficult, but perhaps the most challenging of all chapters, because within this chapter you'll have a look at new tools and new ways to represent mathematical objects that you've never heard of or might have heard of in the past, but it was never properly defined for you. So we're going to talk a lot about vectrices, components of vectrices, matrices. We're going to introduce a new concept known as vectrices, which is a mix of matrix and vectors. So quite interesting concept. We're going to revisit Coriolis acceleration. We're going to talk about Newton's laws and things like that. Okay. Then in chapter 2, we're going to build upon these newly introduced tools to look closely at the two-body problem, which only considers the spacecraft and its primary attracting or its primary gravitational body around which the spacecraft is orbiting. So we're not going to talk about perturbations in this chapter, so we're going to only focus on, the fundamental of orbital mechanics, which is no perturbation, only a gravitational force which is acting on the spacecraft. And this is known as the Keplerian two-body problem. Then in chapter 3, we're going to make things a bit more realistic by introducing orbital perturbations. So we're going to look at the effect of drag on the trajectory of the spacecraft. We're going to look at the effect of J2, which is the adverse effect caused by the oblateness of the Earth, things like that, and analyze their effects on the Keplerian motion. Chapter 4, we're going to look at how can we apply orbital maneuvers to change the orbit of a spacecraft and make it a new orbit. So for example, how can we go from a circular orbit around the Earth up to an elliptical orbit, for example, or vice versa? So how can we apply those maneuvers? At which point of the orbit they have to be applied will be the core of chapter 4. Finally, chapter 5, probably the most interesting, at least from my point of view, is the one that's going to deal with spacecraft formation flying. The reason being that this is closely related to my research activities in the lab. So again, formation flying will analyze now the relative motion of one spacecraft with respect to another. And then we're going to derive the equations of motion from first principle. And also we're going to look at tools that allow us to design a specific formation around the Earth. Okay? Now, in terms of the course format under the COVID pandemic, this course will be delivered in a blended fashion, meaning that all the lectures will be posted online on YouTube. And I'll talk about that in a moment in a subsequent slide. So that's the online portion of the course. The in-person aspect of the course will be for the PA sessions, which will be held every Monday, 11:35 to 12:25. So again, we're going to have in-person activities as well as virtual activities. So that's why it's called a blended method of delivery. Now the lecture notes are all available on Brightspace. They were posted last week, first week of September. So everything is there for you, including the course outline, the lecture notes, which are organized in a single PDF document. So everything is on Brightspace right now. Good news about this course is that you won't need to buy any textbooks because the course notes are self-contained. It's worth mentioning though that there were designed based on this list of textbooks here. Okay, so for the keeners among you, you could cherry pick if you really want to have a textbook to refer to. I don't have anyone in particular in this list. They're all very good and solid foundational textbooks in orbital mechanics, and they were all used to design the course. So for those of you who are thinking already about grad school in this area of study, then perhaps you could go back to this list and order a few, if you will. The lectures. Now, under regular circumstances, every lecture would be 80 minutes in duration, but because of the online format and the asynchronous method of delivery for the lectures, they were all pre-recorded in my basement, and which means that the duration varies between 60 and I'd say maybe 90 minutes, more or less. Again, pre-recorded. They will be posted on Brightspace twice a week. Or maybe I'll decide at one point to just drop them all off and be done with it. But to begin with, I'll spoon feed you with the lectures. So 2 links will be posted on Brightspace per week, and these are YouTube links, so you'll have the chance to watch the videos in high definition on YouTube. So the objective of these lectures is obviously to present the theory of the class, and essentially what I'm doing with you is to derive the equations as they appear in the lecture notes. So I'm working on the whiteboard and I'm deriving equations after equations. I don't use any PowerPoints for this course. That's the first and the last one you'll see. So everything else will be whiteboard discussion and equation derivation. I really feel and I'm convinced that that's a good way for you to learn. So the pace at which I deliver the theory is more digestible by you guys. So yeah, I really hope you'll enjoy the lectures and the way I teach. So that's for the lectures on Brightspace that will guide you through YouTube videos. Now the PA sessions, all we have is 50 minutes once a week. So every Monday, 11:35 to 12:25 p.m. Not a.m. obviously, that's a typo. So here you have a choice. Either you join me in person in Minto 2000 for 50 minutes while I'll just walk around the room and answer any questions you might have about, anything anything related to the course. Could be about the lecture material, could be about the problems. Because yes, you do have problems to solve, and the objective of those problems is to get ready to write the midterm and the final exam. So if you're struggling with a particular problem, just show up, to those PA sessions and, ask me questions, and I'll be more than happy to give you a hand. So it's not one of those where I spend 50 minutes just deriving solutions to the problems on the board. It's more like a discussion between all of you and me. So I'll walk around and I just answer questions on the fly. And if I feel that there's a need for me to go to the board, I'll do so, but that's not from the get-go. So that's one option. The other option would be to join a live session. So if you don't feel comfortable going to campus in person under the COVID pandemic situation, no problem. You can join the PA session that will be delivered simultaneously, every Monday, 11:35 to 12:25. The only difference is that, well, the obvious one being live or virtual session instead of in person. But the other difference is that the TA will handle the virtual session on Zoom as opposed to me handling the in person. So you can choose whatever PA session you wish to attend, and feel free to mix and match. If on a given week you don't feel that going to campus, you can join the TA for the virtual session online on Zoom. And if the next week you feel like coming to campus talking to me, just do so and show up to Minto 2000. So the way that these PA sessions are handled, again, I've already said that, but I'll just answer questions about the theory or practice problems. Speaking of the practice problems, you may have noticed that they are found at the end of each chapter, included in the lecture notes document. And that's the PDF document that was posted on Brightspace last week. Now, because our first official lecture was today, and all we're doing today is to go over the course outline, that means that next Monday you won't be ready to tackle any problems. So there's no PA session next Monday. So they will begin officially on Monday, September 20th at 11:35, either in person or virtual with the TA. Okay? Now, evaluation. The way it's going to work is that you have both a midterm and a final exam, 30% and 40% respectively, as well as an assignment. So the assignment is very simple. It only consists of you collecting the solutions to a set of particular problems included in the lecture note document. And those problems that you have to hand the solutions are indicated by asterisks. So if you look at the list of problems in the lecture note documents, you'll notice that some have little asterisks next to the problem numbers. That means that that's one of those that you have to handle me the solution at the end of the semester. So all you do is that you collect them all in a PDF document and you send that to me by email by the deadline. Okay? STK, Satellite Toolkit. For those of you who are interested in working in the space industry, one of the softwares that is found almost in all organizations, at least in Canada, is STK. Okay, so STK is a visualization software that allows you to visualize in 3 dimensions the orbital motion of a spacecraft around the Earth, among other things. So because it's highly valuable for you to learn the software, I decided to give you 5% bonus mark should you get certified. The only thing, or the catch, I guess, is that because we don't have time in this course to go over the software and explain you how it works, this is something that you would have to do on your own. And again, this is optional. It's not mandatory, but I highly recommend that you do it. So the way it's going to work is that you're going to go to the website, and all the details are in the lecture note documents. And you download a free version of STK, and you complete tutorials online. And once you're ready, you do an online exam, which is I think it only consists now of you creating different scenarios for orbital motion. And then you submit your scenarios to STK. They will mark your exam and send you back the result. And if you pass, then you forward me your certificate to indicate that you've indeed passed the exam, and then I'll grant you 5% bonus mark. In terms of number of hours you have to put in to go through the tutorials and write the exam and things like that, I think it's been a while, but I'm pretty sure it can easily be done over a weekend. So it's not something that would take you weeks and weeks to do. It can be done in just a few hours over a weekend, for example. Okay? Now the assignment, which is again just a collection of all problems, well, not all, but a subset of all problems included in the lecture note documents. You'd have to hand that in by Friday, December 10th. 5 p.m. by email. And again, that's the solution of all MATLAB Simulink related problems. And these are indicated by an asterisk in the document. And also to make sure that you just didn't copy your friend's solutions, I ask you to provide the code that you've used to generate your solution as an appendix. Okay? That's for the assignment. The midterm is going to be closed book. 80 minutes is going to be done in a virtual fashion during a lecture session. So that's going to be held on Monday, November 1st. So right after Halloween. And then the final exam is going to be closed book, 3 hours, also delivered in an online fashion. The time is yet to be determined because I'm not selecting the date and time for that. This is all handled at the university level, so you'll get more details in future about the final exam. Yes, MATLAB Simulink. So as I mentioned, it is required to solve the assignment because the assignment is a collection of all MATLAB Simulink related problems. But that being said, it is not required for any exams. Okay? So it is only for the purpose of completing the assignment. So in the past, students had access to MATLAB Simulink on campus, on the computers. All computers have MATLAB Simulink installed in the department, but because most of you will be working remotely, that probably means for that you'll have to have your own license installed on your laptop. Good news is that Carleton makes available those licenses to you as a student. So all you have to do is to go to the Carleton ITS website and just download the license, I guess. If you have any questions about obtaining a MATLAB Simulink license, reach out to me or Neil in the Mech and Aero department, but it should be pretty obvious from the Carleton ITS website. STK is not required for this course, although again, I highly recommend that you complete the STK certification and get your 5% bonus mark. But that's the only time that you'll have to use this software in this course, should you choose to complete the certification. So that's a website that you can go to get a flavor or an idea of what STK is all about. I'm not going to play that for you, but you can access the website later on. Okay, so if you want to get in touch with me or learn more about my research activities and things like that, just navigate to carleton.ca/spacecraft. That's my research lab website, where you'll have also all the information to get in touch with me. That's my email address that you see on the slide. So that's steve.ulrich@carleton.ca. Whenever you're sending me an email asking about whatever, make sure that you use Aero 3240 in square brackets and then column as a subject, and then whatever the email is all about. So question about vectors or midterm concerns or things like that. because otherwise it's going to get lost in all the emails I get on a daily basis, and I get quite a few, as you can imagine. But whenever I'm going to see Aero 3240 in the subject, I'm going to give it my highest priority. So typically I do my best to answer your emails within 24 hours. Okay. So don't forget, use my email address here, not the Cmail or something else. It's at carleton.ca, and use Aero 3240 in the subject. Otherwise, there might be delays. Academic accommodations. Should you require any accommodations, let me know as soon as possible so that we can discuss about that and reach a solution together. But the full details about accommodations is included in the course outline, which is part of the PDF document I posted on Brightspace. Okay, so yeah, with that concludes the course outline. So hope that you'll have a fun time going through the course. I know you've been waiting for a long time to get to your first Aero-D specific course. So here you are. So I'm super stoked to be spending the semester with you teaching orbital mechanics, and hopefully I'll see a lot of you in person during the PA sessions. Otherwise, get in touch with the TA for the PA sessions, and all the best. Take care.